Think about how different dog bites man is from man bites dog. Same words, new meaning. In this topic, we'll explore why order, timing, and context matter so much for language, signals, and time series, and how that prepares us to build powerful sequence models. You've already seen how machine learning and deep learning learn patterns from data, and where transformers fit in that picture. Now we're zooming in on sequences like text and time series, where order and context change meaning. From here, we'll trace how classic sequence models evolved step by step into transformers. Sequential data is all about order. If you shuffle it, you don't just rearrange it, you actually change its meaning. Think of words in a sentence, notes in a song, or daily stock prices. Each item depends on what came just before and after. That's why sequences capture patterns, trends, and structure over time. Compare that to classic spreadsheet data, where each row is usually an independent example. One customer, one loan, one transaction. Shuffle those rows and your prediction problem barely notices. Many traditional algorithms are built on this independence assumption. Sequences break that assumption. The order itself carries meaning. Words in a sentence, notes in music, clicks in a session, rearrange them, and you change or destroy the signal. Sequence models are specifically designed to capture these positional dependencies. Text is a perfect example of sequential data. Every sentence is a sequence of words, and every document is a sequence of sentences. Change the order and you change the meaning, or even lose meaning altogether. Modern language models work with tokens, pieces like words or subwords, but those tokens only make sense in sequence. Sequences show up everywhere, not just in text. Audio is really a long list of amplitude values, one after another in time. Sensors continuously stream readings as a sequence. Financial markets form time series as prices and volumes move step by step. In all of these, what matters is how values change, repeat, or trend over time, rather than any single measurement by itself. Order in language isn't decoration, it's structure. Swap dog and cat, and you've changed who's doing the chasing. Same vocabulary, different story. The same happens with questions and statements. You are coming becomes are you coming? Just by moving words around. Sequence models need to detect these patterns or they'll misunderstand who did what to whom. Language models also have to read the room, not just memorize word meanings. The word bank means very different things in riverbank and bank account. Pronouns like he or it only make sense if you remember who came earlier. Even sentiment or sarcasm can flip with tiny changes in context. Take a second and mentally complete these sentences. I saw her duck. Did you imagine a bird or someone suddenly lowering their head? This movie is sick. Are we praising it or complaining? Now tweak a sentence. I don't like this versus I like this. One tiny word flips the meaning. Language is fragile like that, so models must read the whole sequence, not isolated words. Whenever your phone suggests the next word, it's doing next word prediction. Given I need a cup of, it guesses coffee, tea, or water based on how language is typically used. Autocomplete goes further, proposing whole phrases. Both tasks demand an understanding of nearby words and the broader sentence, which transformers handle especially well. Sequence models go beyond next word prediction. They capture meaning across the whole input. For sentiment, the tone might flip at the end. I thought I'd hate it, but I loved it. The model has to keep both parts in mind. For translation, it must track grammar, word order, and long-distance dependencies across languages. For summarization, it distills many sentences into a shorter version while preserving the main ideas and logical flow. Sometimes the key clue in a sequence appears long before we need it. A character's name might be mentioned once, then referenced pages later. A variable could be defined at the top of a file and control logic far below. These far-apart connections are long-range dependencies, and good sequence models must capture and relate them reliably. As sequences get longer, early information has to be passed from step to step through a hidden state. Each step can slightly distort or weaken that signal. Over many steps, it may fade almost completely, or occasionally blow up. The result is limited memory. the model can simply lose important context from far back in the sequence. Over time, sequence models have evolved along one big dimension: how much context they can see. N-grams and simple RNNs mostly attend to nearby neighbors, so distant information fades or gets forgotten. LSTMs and GRUs extend that memory, but they still pass information step by step, which becomes hard to scale. Transformers break that chain, letting any position connect directly to any other. This shift from local to global context is what enables modern language models. We've seen that sequences aren't just data points. Their order and context carry meaning. Language in particular needs models that capture relationships across long spans, and many real tasks fail if models forget earlier information. In the next section, we'll follow how classical methods led to RNNs and LSTMs, and how their limitations motivated attention and transformers.